Welcome to week 6 of the NPTEL course on functional programming in Haskell. In this lecture, we shall be introducing recursive data types. Just like we have recursive functions in Haskell, we can also have recursive data types. A recursive data type T is one which has some components that are of the same type T. This means that some constructors of a recursive data type T have T among the input types as well as the return type, of course. Here is a simple example of a recursive data type, that of natural numbers. We know that Haskell offers a built-in type of int, integers, etc., but these represent both positive as well as negative numbers. In this example, we want to represent the non-negative numbers, that is 0, 1, 2, 3, etc. Here is how we could do it. Data nat equals 0 or successor nat. This is the data declaration. We see that nat is the type constructor or the name of the type, and 0 and successor are the value constructors. 0 is a value constructor that takes no arguments at all, whereas successor is a value constructor that takes a natural number as argument or an object of type nat as argument and returns an object of type nat. As you can see, 0 is of type nat, successor is a function from nat to nat. We could now define functions on the type nat by using pattern matching as usual. For instance, here is a function that checks whether an object of type nat is 0 or not. Is 0 is a function from nat to bool. Is 0 of 0 is true. Is 0 of successor of anything is false. Here is a function that computes the predecessor of a natural number. By convention, the predecessor of 0 is taken to be 0 since we do not allow non-negative numbers. So pred is a function from nat to nat. Pred of 0 equals 0. Pred of successor of n equals n. We could have other similar definitions. For instance, here is a definition of the plus function, which takes two nats as inputs and produces a nat as output. This function is defined using recursion. Plus m0 equals m plus m successor of n equals successor plus mn. Recall that plus mn returns a nat as a result, and successor, recall, is the constructor that takes a nat and produces a nat. So successor plus mn produces an object of type nat. Here is the multiplication function defined recursively. Mult m0 equals 0. Mult m successor of n equals plus of mult mn and m. This is just saying that m times n plus 1 is the same as m times n plus m. Here is a second example, another simple example of a recursive data type. This is the example of lists. This example also shows that recursive data types can be polymorphic. Here is the data declaration. Data list A equals nil or cons A list A. Recall again that nil and cons are the value constructors and list is the type constructor. This is just the built-in type list A that is provided by Haskell, but we are providing this definition just as an example. The functions are defined as usual using pattern matching. Head is a function that takes a list of type A as input and produces an object of type A as output. Head of cons x anything is x. Notice that this function fails when you invoke head on the list nil. This causes an exception on head nil. You can have your own preferred behavior. For instance, head is a function from list A to maybe A. Head nil equals nothing. Instead of not providing any definition for head nil, you define head nil to be nothing, and you define head of cons x anything to be just x. Here is a third and maybe more challenging example, that of binary trees. A binary tree data structure is defined as follows. The empty tree is a binary tree, and a node containing an element with a left and right subtree is also a binary tree. So the definition is as follows. Data B tree A equals empty or node B tree A and another argument which is a B tree A. So again recall that empty is a function which doesn't take any inputs and whose output is an object of type B tree A. Node is a function with type signature B tree A, arrow B tree A, arrow B tree A, which is the tree that is returned. Yeah, that is explained here. Empty is a function with type B tree A. Node is a function of type B tree A, arrow B tree A, arrow B tree A. Here is an example of a binary tree. Node of a left subtree, and the value at the node is 3, and there is a right subtree. The left subtree is recursively given by node and a left subtree of it, and here is the value at the root of the left subtree, which is 2, and here is the right subtree of the left subtree. In this case, the left subtree here and the right subtree here are empty. Similarly, the right subtree of the bigger tree with root 3 is node mt5 empty. Here is another example. Node of some left subtree which is given by node mt4 empty, and the root is 6, and the right subtree itself is a non-trivial tree. Node of some left subtree and the root value being 3 and its right subtree being node mt5 empty. This tree would be defined as this. Node of node mt2 empty, which defines this left subtree, 3 which defines the root, node mt5 empty which defines this right subtree, which consists only of a single node. Here is another example. You have a binary tree with 6 as root, 4 as the only node in the left subtree, and the right subtree consisting of 3 as the root, 2 as the only node in its left subtree, and 5 as the only node in its right subtree. This would be defined as follows. Node of node mt4 empty, 6 node of node mt2 empty, 3 node mt5 empty. The structure should be fairly simple now. Here is another example. This tree is node of a fairly large left subtree, a non-trivial left subtree, and the root value being 4, which is declared here, and a right subtree which has only a single node. The right subtree is node mt5 empty. The left subtree itself is a tree which is of the form node 2 and a left subtree which says node mt1 empty and a right subtree which says node mt3 empty. This is how you represent binary trees. Now you can define functions on binary trees as usual by using pattern matching. Here is a simple function on binary trees. The function size, which returns the number of nodes in a tree. Size is a function with signature b tree a arrow int. Size of empty equals 0. Size of node tlx tr. TL represents the left subtree, tr represents the right subtree, x denotes the value at the node, equals just the size of the left subtree plus 1, because the root is also a node, plus the size of the right subtree. Here is another simple function on binary trees, height, which gives the longest path from root to leaf. Height is a function with signature b tree a arrow int. Height of empty equals 0 because there are no nodes at all. The root is the same as the leaf. Height of node TLXTR equals 1 plus max of height TL and height TR. If the left subtree had height 4 and the right subtree had height 3, then the tree itself would have height 5, because 5 is 1 plus max of 4, 3. Here is a function which reflects the tree on the vertical axis. For instance, you start out with 4 left subtree having 2, 1, 3, the right subtree having just the node 5. If you reflect it, the left subtree will now have a single node 5 and the right subtree will have the reflection of the left subtree here. So you will get 2, 3, 1 instead of 2, 1, 3. How would you define this? Reflect a function with signature b tree a, arrow b tree a. Reflect of empty equals empty. Reflect of node TL x TR is node reflect TR x reflect TL. Notice that you form the node with the reflection of the right subtree on the left and the reflection of the left subtree on the right. Here is another function. We want to list all the nodes in a tree level by level and from left to right within each level. So in this tree there are 3 levels. This is one level, this is another level, and this is the third level. And we want to list elements from the first level and then from the second level and then from the third level, and within each level from left to right. So levels on the above tree would yield 4, 2, 5, 1, 3. So levels is a function which has signature b tree a arrow list a, and it's defined as follows: levels t equals concat of my levels t. Recall that the concat function takes a list of lists of type A and produces a list of type A. So my levels t ought to be a function that returns a list of type A. My levels is a function with signature b tree a arrow list of A. This list is supposed to represent the first list in this list represents all the nodes in the first level. The second list inside this list represents all the nodes in the second level, etc. So my levels of empty is nothing but the empty list, because there are no levels in an empty tree. My levels of node T1 x T2 is the list that you get by prepending the list containing x, because x is the only node in the top level. So the list consisting of x should be the first list in this list of lists, and following that you have a bunch of lists that you get from my levels T1 and you have a bunch of lists that you get from my levels T2. You join the lists at the appropriate levels. So the definition of my levels node T1 x T2 is the list consisting of x coming in front of join of my levels T1, my levels T2. The code for join is given here. Join is a function which has signature list of A, arrow list of A, arrow list of A. Now the function join is very similar to zip width of plus plus applied to XSS and YSS, but there is a slight difference in this case. So let's look at the definition in a bit more detail. Join of empty list YSS equals YSS. In the case of zip width, this would have been empty list. Join of XSS empty list equals XSS. These two cases represent the situations where the left subtree has fewer levels than the right subtree, and this represents the case where the left subtree has more levels than the right subtree. Now join of XS followed by XSS and Ys followed by YSS is just x's plus plus y's coming in front of join of xss and yss. So this completes the definition of levels. Let's look at how we can display trees. So a simple way of displaying trees is to say deriving equality and show, is to say deriving show in the data type declaration. But the default show method on trees is very hard to parse. For instance, show of this complicated tree is just the same representation given inside quotes. As you can see, this is not very easy to read. We might want a prettier show with a better layout. For instance, suppose we define tree 1 to be this tree, node with root 6 and left subtree consisting of a single node 4 and right subtree consisting of root 3 with left child 2 and right child 5. Then typing tree 1 in GHCI should give us this. This is the desired behavior that we want. In this, we see that each node is printed on a line, and there are 2n spaces before each node at level n. Here we are assuming that the root is in level 0. So 4 and 3, which are nodes at level 2, have 2 spaces before them, and 2 and 5, which are nodes at level 3, have 4 spaces before them. And this layout makes the structure of the tree clear. 6 is the root with 2 children 4 and 3. 4 doesn't have any children, whereas 3 has children 2 and 5. You can see that the printed layout mirrors the structure of the tree and makes it pretty clear. 6 is the root, 4 and 3 are the children, 4 doesn't have any children, 3 has 2 children, 2 and 5. Here is another tree, 4 with left subtree consisting of 2, 1 and 3 and the right subtree being a single node 5. We want this to be laid out in this fashion, 4 with 2 children 2 and 5, and the children of 2 immediately displayed on the lines following 2, 1 and 3, and 5 displayed after that. But you can look at which column 5 appears in and determine whose child it is. 5 is the child of 4 because 5 appears in column 3, whereas 4 appears in column 1. Here is another tree. This is a tree with root 6, left subtree consisting of a single node 4, right subtree having a node 3 whose left child is 2 and whose right child is 5. This is laid out as follows: 6 followed by its 2 children 4 and 3, followed by its left child which is 2, whose children are displayed here as star and 5. This is because this node has only one child and the other child is empty, and we use star to denote which child is empty in case there is only one child. In case both childs are empty, as in the example of this node 4, we do not display anything. But if one subtree is empty and the other subtree is non-empty, then we display a star corresponding to the subtree that is empty. So 2 has left subtree which is empty and right subtree which consists of a single node 5, and 3 itself has this as the left subtree 2 star 5, and its right subtree is empty which is denoted by star. Now how do we define this show function? We define it as follows using an instance declaration. Instance show A implies show B tree of A, where show T is the tree here, is just draw tree T empty string. Draw tree will draw the layout of the tree where the second parameter, which is a string, tells how many spaces to insert before drawing the current subtree. So draw tree is a function with signature show a implies b tree a arrow string arrow string. This string is the number of spaces that have to be displayed before the current subtree is displayed, and this string is actually the output, the layout of the tree. Draw tree empty, this is the empty tree, spaces equals spaces plus plus star backslash n, which denotes the new line character. You will see that you will encounter this case only when this is the sole empty subtree of a node. The other case is when you have a node x, both of whose subtrees are empty, node nil x nil. Draw tree of node nil x nil spaces is nothing but spaces plus plus show x plus plus new line. Draw tree of node TL x TR, where TL is the left subtree and TR is the right subtree, spaces is nothing but spaces plus plus show x plus plus new line. Remember that we always add this many spaces before displaying the current subtree, plus you append that with draw tree of TL, but when you draw the left subtree you have to add two more spaces, so which you do by adding two spaces to the beginning of this list, and then you concatenate that with draw tree of TR, which is the right subtree, again giving two spaces, adding two more spaces in the beginning of laying out the right subtree. So in summary, recursive data types have been introduced in this lecture. They are a very important concept in Haskell. A recursive data type T is one which has some of its components of the same type T. And we have seen two canonical and important examples of recursive data types, lists and trees. In the next lecture, we will see more on trees.